Welcome to Lecture Online, and here we're going to do a series in astronomy where we talk about how we discover how far things are, how big things are, how bright things are, and what we discover when we try to do that, and what people have discovered for thousands of years. The biggest challenge in astronomy always has been to figure out how far things were. And let me show you why that is such a big deal. For example, let's say there's two different stars, one that is a really big star but it's far away, the other one that's a much smaller star but it's much closer to us. The way we judge sizes in astronomy is by figuring out how much of an angle the object subtends. So when we look at it, we draw a line from our eyes to the left side of the object, we draw a line from our eyes to the right side of the object, and so the two lines form an angle between them. If the angle between them is big, then we're looking at something that appears very big to us. If the angle between them is very small, then we look at an object that appears very small to us. But we won't know actually if the object is really big or if the object is really small, because we don't know how far away the object is. In this case, notice that this object, even though it's much bigger, has the same angle, it subtends, as we say, the same angle as the smaller object that's much closer. So to us, the two objects will look exactly the same size, and so we're going to assume that they're the same size and maybe even assume they're the same distance. We really don't know whether or not one is farther away than the other. Maybe this was a really big star really far away, so it looks small, we just don't know. And so that was always the biggest challenge. The biggest challenge is how far is everything that we look at in the universe. Here's another example. Let's say that we have a really bright star. Usually stars are bright in part because they're very large, but also in part because they're very hot, and we'll see that in a later video. Here's a much smaller star, and so the brightness ascribed to a star is considered what we call the absolute magnitude. So this is indeed a very bright star. It has a very large absolute magnitude. This is a smaller star. It has a much smaller absolute magnitude. But what we see from the Earth when we observe stars in the universe, we see what we call their apparent magnitude, how bright they appear to us. So in this case, both stars will appear to have the same what we call apparent magnitude. They will look the same brightness, even though this one is much brighter than the other, simply because this one is much farther away than this one. So they appear the same brightness, but they don't have the same brightness. And the question again is, how do we figure out which one is the bright star and which one is the dimmer star? Which one is the bigger star? Which one is the smaller star? And it really comes down to it is if we can just know how far the stars were. If we knew how far they were, then it would be really easy to figure out, oh, they look the same brightness, but this one is much farther away, so therefore it must be a lot brighter. Or, oh, I know how far they are, this is much farther away, but since it has the same angle, it must therefore be much larger. So it always came down to knowing how far things were in the universe. And so that was the big quest. And what we're going to do in the next so many videos is look and see how people used very clever methods to figure out how far things were, which were then they were able to figure out how big things were, how bright things were, and so forth. A lot more could be known about everything in the universe if we just could figure out how far things were. And you'll see over thousands of years how people struggled and strove to find out how far things were. And they came up with some really clever methods, and you'll be interested to see what some of those methods are. So if you're interested, stay tuned and look at the next so many videos. See you then. Welcome to Lecture Online, and here's our first quest. Not ours, because we didn't do it, but Eratosthenes did it. And the first quest to figure out the size of the Earth. And this was back in the day when most people thought the Earth was flat. If you went too far to the edge, it might fall off. But some Greeks, including Eratosthenes, believed that the Earth was round, and he was interested in figuring out how big the Earth was. And he had a very clever idea to figure that out. What he noticed was when they went to the seaport of Alexandria, which is on the Mediterranean coast, this is a big city in Egypt on the delta of the Nile, and they looked inside a well on June 21st, which is when the sun is at the highest point above the sky before it begins to sink down again because of the tilt of the Earth. Then they looked in the well and they noticed that the angle that the rays of sunshine made going into the well made about an angle of 7 degrees, more like 7.15 degrees with the vertical. At the same time, he had heard, and he went and checked, that when you go to the city of Syene, which is a distance up the Nile River, which is pretty close to where the Aswan Dam is built today, and you looked into a well on June 21st, you would find no shadow at all. The sunshine would light up the water at the bottom of the well completely, so that meant that the sun rays were coming down vertical from the sun directed towards the earth, and there was no angle between the vertical and the sunshine. So he realized there was an angle of 7.15 degrees between Alexandria and Syene on the Earth's surface if the Earth was indeed round. He then surmised, of course, that if you go all the way around the Earth, you would cover an angle of 360 degrees. So the question was, the ratio of the distance between Alexandria and Syene to the angle 7.15 degrees is equal to distance all the way around the Earth to 360 degrees. Let me write that down so it makes a little bit more sense. So the distance from Syene and Alexandria between Alexandria and Syene is about 5,000 stadia. Stadia is the distance that they used back then in Greek days, and it was assumed to be about 185 meters. Now, I believe that there is different distances ascribed to a stad, and there were some distances that were less than that, like 167 meters, something like that. But I think the most popular interpretation of the distance one stad was about 185 meters. So what he said was that the ratio of the angle, 7.15 degrees, to the distance between the two cities, which was about 5,000 stades, or stads as they called them, is equal to all the way around the Earth divided by the complete circumference of the Earth. So it's simply a ratio between those two quantities. See if I write circumference correctly. There we go. All right. So now all we had to do, or all Eratosthenes had to do, was figure out how far it was between Alexandria and Syene. And of course, there had been a lot of travel between those two cities with camel trains, and sure enough, the distance was roughly always known to be about 5,000 stadies. So what they did was they took that ratio, and when they calculated the circumference, they said the circumference was equal to, and of course that would be 7.15. No, I'll take that back. Difference would be 360 degrees divided by 7.15 degrees times the distance between those two cities. And when he calculated that, he came up with a distance of 252,000 stadies. Now, if we ascribe the distance of 185 meters to that, see here, 252,000 times 0.185 kilometers, we come up with a distance of 46,640 kilometers, when the actual value for the size of the Earth, the circumference of the Earth, was 40,000. So 40,000 was the actual. But then they said, well, not everybody ascribed the distance of one stadia to 185 meters, especially in Egypt. They had a different distance, and I'm trying to think of what the distance was, but I think it was somewhere in the neighborhood of 167 meters or so. So if we take 167 times 252,000, we get a distance of 42,000 kilometers. So you can see that he actually wasn't that far off when you think that this was done in a kind of a very primitive way. So Eratosthenes had a pretty good idea how big the Earth was already more than 2,000 years ago. Now, he lived a long life. He was born in 276 BC. He died in 194. That means he was 82 years old when he died, which is pretty old in those days. But during that time, he came up with amazing things, including figuring out the size of the Earth. So he knew the Earth was round, and he knew pretty well how big the Earth was. And the question always is, did Columbus know how big the Earth was? Because when he set sail across the Atlantic Ocean, thinking he was sailing to India, if he had known what Eratosthenes knew, would have done so. Would have told the sailors, oh, it's 12,000 miles of open ocean to get to India. Don't worry, we'll get there. We know the Earth is round. Don't know. That always will be a mystery to figure out if Columbus actually knew how big the world was the way Eratosthenes did. Anyway, that was one of the big challenges, and that's how it was overcome. If you like this, stay tuned, and we have some other big challenges for you to figure out how big the moon was, how far the moon was, how big the sun was, and on and on and on. Astronomy, pretty challenging to figure out how far things are. Welcome to iLecture Online. Now imagine you lived more than 2,000 years ago, and most everybody around you thought that the Earth was flat. And they looked at the moon, they really didn't know what it was. And someone came around and says, try to figure out how big that thing up there is. How big is the moon up there in the sky? And you would be perplexed. You'd say, wow, I wouldn't even know where to start. But there were some smart people back then. One of them, his name was Aristarchus. He was a Greek who lived between 3010 and 230 BC. And what he surmised was, first of all, that the sun was much bigger than the moon and the earth. And he assumed that the sun was at the center of what they knew then was the universe, and that the earth revolved around the sun. And he also assumed that the moon revolved around the earth. And so he surmised that once in a while, since there's a total solar eclipse, when the moon moves in front of the sun and blocks the light to the earth for some small portion of the earth, at that location right there, and usually just a small sliver on the surface of the earth, there's a total solar eclipse. The moon completely covers the sun's disk and it becomes dark like nighttime just for a few minutes. And they knew that happened in regions around the world once in a while, and when it happened, it was only in a very small specific region. So the conclusion they drew was that the shadow of the moon was tapered, and by the time the shadow of the moon reached the earth, it had gone down to just a very small region. So they figured that the taper of the shadow was a known quantity. So then what they said was, well, on the other side of the earth, once in a while, the earth blocks the sunlight for the moon, and then we have what we call a total lunar eclipse. But when that happens, we can see the moon slowly disappearing into the shadow of the earth, staying there for a while, and then eventually reappearing on the other side. And they assumed that that distance, of course, from the earth to the moon would be the same as from the earth to the moon on the other side. And so they assumed that the earth's shadow tapered in the very same way, in such a way that the diameter of the earth right here would be diminished, or at least the shadow of the earth would be diminished by 1 moon diameter by the time it reached the position of the moon. So what he assumed then was that this right here was a half a diameter of the moon, and this was 1/2 diameter of the moon, so together forming a full diameter of the moon, which is the amount of taper the moon shadow has by the time it reaches the earth. And then what they would do is they would watch and measure how long it would take for the moon to completely disappear into the shadow of the earth. They could sit there. They didn't have stopwatches back then, but they had a way to measure time. And so they would watch how long it would take for the moon to completely disappear into the shadow, and then how long it would take for the moon to reappear on the other side. And based upon the rate of the moon moving in there, they could figure out that this distance right here was about 2.5 diameters of the moon. So they added everything together and they said, well, that means that the earth right there, the diameter of the earth, therefore is equal to 2.5 plus 1/2 plus 1/2, or the diameter of the earth was equal to 3.5 times the diameter of the moon. So diameter-wise, they figured out back then, more than 2,000 years ago, that the earth was about 3.5 times the diameter of the moon. And from that information, eventually they also figured out how big the moon was, not how big the moon was, but how far the moon was and so forth. So we'll get into that in another video. But the amazing feat was that with studying total solar eclipses and total lunar eclipses and making some very careful measurements, they were actually able to figure out the rough size of the moon relative to the earth. And since Eratosthenes had figured out the size of the earth, it was a small calculation then to figure out the size of the moon. Amazing stuff. And when most people on the earth thought the earth was flat and in the center of the universe. So quite something. Okay, welcome to iLectureOnline, and here we're continuing with discovering the challenge that people had to figure out the size and the distance of things in astronomy. And so the next challenge was, how far is it to the moon? Now, Aristarchus had already figured out how big the moon was in a very ingenious way. During a lunar eclipse, he figured out how far or how long it took for the moon to travel through the Earth's shadow. He knew that the Earth's shadow had the same shape as the moon's shadow during what we call a solar eclipse, and so therefore he figured out that the Earth's diameter was 3.5 times the moon diameter, and that information was important. Another thing that he observed was that during a solar eclipse, as the moon passed through between the sun and the Earth, he could see that the moon would completely block the sun's disk, and that the size of the moon's disk was about the same as the size of the sun's disk at that very moment. So they had about the same angular size. Through some calculations, which we'll explain in a different video, he did figure out that the sun was approximately 20 times as far away from the Earth as the moon. Now, of course, we know that's not at all the case. It's more like 400 times as far. So he's way off. But at least he had kind of an idea of how to do that, how to figure that out. And so therefore, he figured if the sun is 20 times as far away from the moon, then the sun must be 20 times as big as the moon as well. And so if the Earth is 3.5 times the size of the moon, and the sun is about 20 times the size of the moon, he figured that the sun must be about 6 times the size of the Earth. Now, he was way off. The sun is way bigger than that. But at least it was a start in the understanding that the thing up in the sky that kept everybody warm was way bigger than the Earth. Now, we're trying to figure out how they figured out how big it was, how far it was to the moon. And the ingenious idea came from this concept here when the disk of the moon was the same as the disk of the sun. They scaled that back and they realized that if they held a small coin up at a certain distance away from the face, then they were actually able to block out the disk of the moon, just like the moon could block out the disk of the sun. And so they were able to measure the size of this thing, and here I drew it. So here's the eye, there's the coin. They were able to measure that angle based upon simple geometry, and they figured out that this distance was 108 times the diameter of the coin. So if they kept it far enough away, a small coin can block out completely the disk of the moon. And so that ratio of that distance to the size of the coin is 108 to 1. And so they surmised that that must be the same ratio for the size of the moon versus the distance here. Now, since they knew that the size of the moon was 1 divided by 3.5 times the size of the Earth, that was the ratio there, so they knew that that 3.5 times the diameter of the moon is equal to the diameter of the Earth, and they figured that this was 108 times the diameter of the moon. From there, they could figure out how far it was to the moon. So let's do that calculation. So distance to the moon was equal to 108 times the diameter of the moon. And the diameter of the moon was 1 over 3.5 times the diameter of the Earth. So that would be the diameter of the Earth. And since we knew approximately how big the Earth was, because of Eratosthenes figuring out with the shadows hitting Cyan, hitting Alexandria, and he figured out the circumference of the Earth, and from that the diameter of the Earth. So if we assume that the Earth is about 3.5, that the diameter of the Earth is about 8,000 miles, so we take 8,000 miles divided by 3.5 times 108, and we get a distance of about 247,000, that would be 247,000 miles, which is actually fairly close to the actual distance to the moon. Now, of course, they didn't know exactly the size of the Earth. Their calculations were a little bit off. But again, you can see that even though they didn't have exact numbers, they now knew fairly well how far it was to the moon. I think their estimate was probably a little bit more than that. But anyway, we were close. So they were really getting on to understanding the size of the universe. Of course, to them, the universe was very local, right? They looked at the moon, they looked at the sun, they saw the wandering planets. They knew the stars were out there, they didn't really know what they were. But at least they began to get the concept of the size of the Earth. They figured out the Earth was round. They figured out the size of the moon. They figured out the distance to the moon. And they already had some idea of how big the sun was and how far was the sun, although their estimates were way off. It took many more centuries before people got more accurate about determining the size of the sun and the size of the moon. Now that we know the distance of the moon, in our next video we're going to see how they first discovered, in a way, the distance of the sun and the size of the sun. Stick around if you're interested, and we'll see it on the next video. Now let's take a look and see how they figured out the distance of the sun. Now this is something that it took people, almost 2,000 years to figure out correctly. But it started somewhere. It started back in the days of the Greek. And again, Aristarchus is the one who really started this whole process and came out with a number. It wasn't bad. It was actually far off, but it was just really an amazing thing to do. And what he did was this. He observed the moon and the cycles of the moon. And at a point where the moon was exactly lit in such a way that we saw exactly a half a moon. So when you look at from the Earth to the moon, and the sun is right here at right angles between the moon, the Earth, and the sun like this, the moon will be exactly half lit as seen from the Earth, And then he figured that the angle made from the sun to the earth would enable him to figure out the distance to the sun. So what he had to do is he had to wait until the moon was in the exact position where he felt that the shadow of the moon was exactly halfway on the left side and the sun side of the moon was exactly halfway on the right side. He then went ahead and looked at the position of the sun relative to the position of the moon, and he figured that this angle right here was an 87-degree angle. Now, back then, looking at the sun, looking at the moon, trying to come up with that angle, that was not an easy thing to do. And from that, he was able to calculate this angle right here. And that's the important angle, of course. Then he said, well, this angle therefore must be equal to 90 degrees minus 87 degrees, which is equal to 3 degrees. And then he realized from geometry, because back then they did not yet know trigonometry, so they didn't know what the sine and the cosine and the tangents were, but they had the similar understanding using trigonometry and using triangles and angles, and they figured out that the ratio of the distance from the earth to the moon divided by the distance from the moon to the sun, which is what he was after, had to be equal to the ratio of that angle right here, the 3-degree angle, divided by the number of degrees in a radian. So he said that must be equal to about 3 divided by 57.3, which is about equal to 1 over 20. Now these are of course rough estimates. So what he concluded based upon that was that the distance from the moon to the sun was about 20 times the distance from the moon to the earth. Now of course we know today that's not the case. Today we know that it's about 400 times, about 20 times as much. But the ability to measure these angles was very difficult. The ability to measure this angle right here was in that time a very difficult task to accomplish. But the fact that he tried it and the fact that he actually came up with a reasonable result was amazing. Now, of course, we had already figured out the distance from the earth to the moon based on the ratio of the shadow, the cone of the shadow, knowing the diameter of the cone at the end and the length of the cone. The same kind of thing where you went ahead and you put a little coin in front of you, blocking out the moon like that, and you measure the distance, you measure the angle right there, and they realized that if you take this little triangle here, that the length of this triangle would be 108 times the diameter or the width of the triangle at the end like that. And of course they figured out the same ratio would be true for the moon like that the diameter of the moon relative to the distance of the moon was also a 108 to 1 ratio. So from that they had to figure out the distance to the moon, and they were actually fairly close to the real value, around 245, 250,000 miles. Now, from that, they then concluded that the sun was 20 times as far, and so therefore 20 times 250,000, so about almost 5 million miles. So they estimated that the distance to the sun was somewhere between 4.5 and 5 million miles. So again, in terms of the size of the universe, that was an enormous accomplishment. They knew that the Earth was about 8,000 miles across. They knew that the moon was somewhere between 2,000 and 3,000 miles across. They knew it was about 250,000 miles to the moon. And now they figured it was about 4 or 5 million miles to the moon. An amazing, to the sun, not to the moon, but to the sun. An amazing accomplishment. Later on, of course, they would come up with better and better methods to figure out the distance to the sun, and they improved upon that. For the next almost 2,000 years, no one improved upon this method, and no one is able to figure out the distance to the sun any better than Aristarchus did. Not until about the 1600s did people begin to devise methods to come up with more accurate measurements. And if you're interested in what those are, then stay tuned and come to the next video and see how they did it then. Welcome to Lecture Online, and now we're continuing in the quest to figure out how they figured out the distance to the sun. And remember, more than 2,000 years ago, Aristarchus figured out that, well, in his way of doing things, he figured out that it was about 20 times the distance from the Earth to the sun as it was from the Earth to the moon. And of course, that put the sun at about 4.5 to 5 million miles, which is about 1/20th of what it really was. But there was no way to improve upon those measurements. What they had to do was wait until the moon was in the exact right position so that the sun will light up the moon on this side right here, so that the side of the moon that is lighted was exactly the same in size as the side of the moon that had the shadow. And from then trying to figure out the angle between the line going from the Earth to the moon versus the line from the Earth to the sun, he figured that that angle made by those two lines is about 87 degrees. And from that, he was able then to figure out that this angle right here was about 3 degrees, which meant that this angle right there was about 3 degrees. And now we have this triangle right here. And you could then say that the distance d between the Earth and the Moon, and the distance d between the Earth or the Moon and the Sun, or the Earth and the Sun, that ratio had to be equal to the angle right here, divided by 57.3, which is the number of degrees in a radian. And that ended up to be 1 in 20. So not until almost 2,000 years later, in 1635, they improved upon that method. It turned out that two very famous astronomers, Nicholas Copernicus, who determined, well, he didn't really determine, but from his logic determined that the sun was at the center of the universe rather than the Earth. It was not a very popular idea in those days. And remember, he lived back in the 15th to 16th century, between 1473 and 1543. And then Tycho Brahe, the Danish astronomer, who was just amazing in making not daily, but nightly measurements of where the locations of the planets were, from which Kepler was able to come up with his 3 laws, who then, Tycho Brahe lived between 1546 and 1601. They also tried to make this very same measurement. And guess what? They came up with about the same results. So almost 2,000 years later, they tried this again, and again they had a ratio of about 1 in 20, thinking that the distance to the sun was about 20 times the distance to the moon. So they were off also by a factor 20. But then something was invented, the telescope. And a famous person, Godfrey Wendelin, who was a Flemish astronomer, came up with the idea to try this with a telescope. When he made the measurements, instead of coming up with a 3-degree angle, he came up with an angle that was less than 1/10 that much, an angle of about 0.25 to about 0.30 degrees. That was the new angle based upon his measurements with the telescope. And so then when he went in and compared that to the measurements that had been made before, he said that, wow, we were off by about a factor of 11. He figured out that the sun was about 11 times as far away had previously been assumed based upon these earlier measurements that had been valid for almost 2,000 years. So now instead of thinking that the sun, the distance between the sun and the moon-Earth system was about 20 times the distance between the Earth and the moon, he now said it was more like 200 to 220 times. He figured they were off by about a factor of 11, which would make that about a ratio of 1 in 220. So now he said that the sun was 220 times as far away from the Earth as the moon was. Now, that was an enormous improvement. Not quite where the sun is supposed to be, because that puts the sun at about 50 million miles, when in actuality it's 93 million miles. But that was an enormous improvement. They really were beginning to figure out the distance to the sun. And so based upon this very primitive method that had been valid for almost 2,000 years, and the new tool, the telescope, they were able to come much, much closer to the actual distance. After that, they refined their methodology. They begin to come up with all kinds of other methods to try and measure the distance to the sun, and then try to find the size of the sun, because once you know the distance of the sun, you could also find the size of the sun. Imagine what people must have thought. Wow, if he is right, and the sun is 50 million miles away, and now realizing that the disk of the sun is the same as the disk of the moon, relative size, of course, in angular size, and you project that out. If you knew how big the moon was, and they knew that, they knew the Earth was about 3.5 times the diameter of the moon, and then they projected that out over this enormous distance to the sun would have then had to be like 50 times as big as the Earth. The diameter of the sun, at that point, all of a sudden became 50 times the diameter of the Earth. This enormous ball there, glowing away, bringing heat to the Earth. Wow, they were really beginning to understand this and discover the sun, the enormous size and enormous distance between the Earth and the sun. But yet, they were still not correct. They were off by about a factor of 2. And so what did it take to come up with a more accurate measurement? Well, if you're interested in that, stay tuned and watch the next video. Here we're going to take a look and see how they came up with an even better estimate as to the distance to the sun. And the way it was done was absolutely ingenious. You must admit, these people were really smart. I don't think there's any way I would have ever figured this out on my own back then if I had lived during that time. But this is how they did it. They used the transit of Venus to figure out the distance to the sun. How in the world did they do that? Well, remember that for almost 2,000 years, Aristarchus is the one who figured out the distance to the sun in a not so accurate manner, and he came up with the idea that it was about 20 times the distance between the Earth and the Moon, and so that made it about 1/20th of the true value, but it gave us an idea. And then it turned out that Godfrey Wendelin, a French, not a French, but a Flemish astronomer, came up with the idea of using a telescope to take the same measurements, and from that we got a much better, more accurate measurement, which now got it to within about half of the true distance, about 45, 50 million miles instead of the 93 million miles. But then, back in 1639, an astronomer from England, Jeremiah Horrocks, figured out that by using the transit of Venus across the disk of the sun, he should be able to figure out the size of the sun or the distance to the sun. And so what that means is, of course, every once in a while, when the moon and when the sun and the earth and Venus are just aligned in the right way, Venus will travel across the disk of the sun. And depending upon where on the earth you are, the Venus will then travel, of course, at a different location across the sun's disk because of your relative angle between where Venus is at, where the earth is at, where the sun is at. So in 1639, Jeremiah Horrocks actually witnessed through a telescope. Of course, he didn't look through the telescope. Bad idea. He allowed the light of the telescope the light of the sun to go through the telescope onto a piece of paper, and he could then see the disk of the sun, and he could then see Venus traveling across the disk. And what he then did was he actually measured the time, how long it took Venus to go across the disk. But that wasn't really important yet at the time, because he was the only one really that then actually took data of that particular transit. He figured out if more than one person did it, and so at least two people did it, or preferably more than two people, living in different places in the earth, or either traveling to those different places in the earth, and then witnessing the transit of Venus from those locations, he would be able to figure out the distance to the sun. So that's what they did. They sent people out to all places around the world, to Tahiti, to South America, Paris, London, wherever they needed to go to get various aspects of that transit of Venus. And so what they would do is they would have a person on the earth right there, another person on the earth right there. They would look at the transit of Venus, and they would measure the time that it took for Venus to travel across the sun. And by knowing the approximate position of where that disk of Venus was, and then measuring the time that it took to go across the sun's disks, they would be able to figure out exactly where the transit occurred on the sun's disk. And they would then be able to figure out the angle between those two locations, simply by doing geometry. And then, of course, they figured out that the angle from the one place on the earth that the observer was, and the other place where the other observer was, if they then took that angle, and that angle would then be subtended between Venus and the earth, that would be the exact same angle from Venus to the sun. And because you can see the line from there going to this transit, and from this line going up to that transit, so they were able to actually, and through Venus, they could actually measure these angles, and then they could say that the relative distance right here on the earth, that d1 divided by this distance between the earth and Venus, let's call that big D1, must equal to this distance right here, which is d2, divided by this distance right here, which is big D2. Now, from Kepler's laws, we knew that the distance between Venus to the sun was about 70% the distance from the earth to the sun. That was Kepler's third law. They were able to figure that out. And so all they had to do was measure this angle by measuring the time that it took Venus to traverse across the sun, by doing some geometry, and by knowing the size of a circle, and they could figure out the distance here, d2. They can then figure out what this angle is equal to, and then they could set up this ratio. And that they knew that the relative distance, that d2 to d1 was 0.7 divided by 0.3. So we can also indicate, and now I'm on to the equal, we can say that the ratio, that d2 divided by d1 was equal to about 0.7 divided by 0.3. Now, based upon those measurements, they were actually able to figure out that distance across the disk of the sun. And from that, they were able to actually find the distance d2 and add that to distance d1 and then get the total distance to the sun. So how did they do that? Again, they took this distance right here and they said that the angle theta divided by 57.3 was equal to the ratio of D1 divided by big D1 right there, which of course had to be equal to the ratio of D2 divided by big D2. And then by using this equation and realizing the relationship between D1 and D2, they can use some very simple algebra to figure out that angle. And from that very angle, they figured out the distance to the sun. And it turned out by using this technique, they finally realized that the distance to the sun was roughly, and let me see what they came up with. Well, they came up with a distance that was roughly between 90 to 95 million miles, which was very close to the actual distance. Actually, I think they were just a little bit short. I think they were actually closer to 90 million. So I think the rough estimate was that it was about 90 million miles, which was just shy of the actual value of 93 million miles. So they were just within a few million miles, and I can't quite remember what the actual distance was, but it was just shy of the 93 million miles. This method finally got them really close to the actual measurement to the distance of the sun. Of course, once they knew the distance to the sun, by using this angle of parallax, or by using the angle between the Earth and the sun, blocking out a ratio of 101:2, so they had this angle right here. Let me draw it. So this angle right here, this angle had a ratio of 108:1, meaning that the diameter of the sun had to be 1/108 the distance. So once they knew the distance, they knew the diameter, and once they knew the diameter, they realized that the sun has a diameter about 100 times, or slightly over 100 times the diameter of the Earth. So now they finally knew how big the sun was. They knew the sun was over 90 million miles from the Earth, and they knew that the Earth would fit into the sun more than 1 million times. Now they understood how large, how enormously large the sun was, how far it was to the sun, and how big it was relative to the Earth. An enormous discovery. So finally, in the 17th century, people were able to make some measurements that really got them in a good direction into understanding how big the sun was relative to the Earth. And it was an ingenious way. Just imagine, they measured the time that it took for the Venus to go across the disk. From that, they knew exactly from a geometry where that they had to occur relative to each other. Then from that, they were able to figure out this angle. And from that angle and the ratios of distances between Venus and the sun and Venus and the Earth, they were able to figure out the distance to the sun. An amazing feat, but that really set us onto the path to understanding our solar system, and from that the rest of the universe. So kudos to whoever figured that out. But Jeremiah Horrocks was one of the main that was very instrumental in figuring out this method and figuring out how far it was to the sun. Welcome to Lecture Online. One of the major contributions to our understanding how to figure out the distances to objects in the universe, and in this case we're talking about the planets in our solar system, was Kepler. Now Kepler shouldn't be given all the credit, because Kepler figured out how to do that by inheriting a notebook from Tycho Brahe, who was a Danish astronomer who spent 20 years of his life very carefully, almost every night when the sky was clear enough, measuring the positions of all the planets in the solar system, trying to figure out the secret to their orbits, the secret to how they moved around the solar system, and of course for us at that time that was the universe. And the mistake that Tycho Brahe always made was that he figured out that he assumed that the planets orbited the sun in circular orbits. That seemed to make sense, right? They seemed to have the circular pattern. And when he took his notes and he looked at the numbers and he tried to correlate them to the assumption that they're going around in circular patterns, just the numbers didn't make any sense. Well, he ended up going to Austria, where Kepler became one of his students. And when Tycho Brahe died, Kepler inherited these notes. Kepler spent years and years and years studying these numbers, studying these notes, and finally he began to understand what they all were saying to him. And so that's where the three laws of Kepler came from. He said, first of all, that planets do not go around the sun in circular orbits, they go around the sun in elliptical orbits with the sun at the foci. So one of the ways to look at it was if the sun is right over here, shining away, and the planets would have these kind of orbits like that, where sometimes they would come in close and sometimes it would be far away from the sun, like in elliptical orbits, with the sun at one of the foci of the ellipses. So that became Kepler's first law. The second law, he realized that when the planets were close to the sun, they moved faster, and when the planets were far away from the sun, they moved slower, in such a way that the area swept out per unit time was always equal. And that, of course, meant that they moved slower there and moved faster there. But the real key to understanding how far things were, especially the distance of the planets, was the third law of Kepler, when he realized that the distance to each planet from the sun cubed equals the period of each planet squared. The period meaning the time it took to go around the sun once. And so here, for the 6 planets that were known, including the Earth, they were able to measure, just simply by observing, that Mercury goes around the sun once every quarter of a year. For Venus, it's about once every 6/10 of a year. For the Earth, of course, it's 1 year. For Mars, it was almost 2 years. For Jupiter, it was almost 12 years. And for Saturn, almost 30 years. But they were able to measure those periods. And so, therefore, we can go back to the formula. If that was true, then all we had to do to find out the distance to the planets was equal to you can calculate that by taking the cube root of the period squared. Now, in order to get the right numbers, the distance would have to be expressed in astronomical units. An astronomical unit is the distance from the sun to the Earth. So if this was the Earth, then this distance would be 1 astronomical unit. The period would have to be expressed in years. Now for the Earth, that makes a lot of sense, because if you put 1 here, 1 squared is 1, the cube root of 1 is 1, so yes, the distance would be 1 astronomical unit. But he figured out that works for all the other planets. For example, if you want to know the distance to, for example, Mars, we plug in this number right here, so we say that the distance to Mars is equal to the cube root of the period, which they measured to be 1.88, in years squared, and that would be the distance in astronomical units. So what we do then is we grab our calculator, 1.88, we square that number, and then we take the cube root of that. And let's see here, cube root, 1 divided by 3 equals, and there it is, 1.5 astronomical units. So that meant they now knew that Mars was 1.5 times as far away from the sun as the Earth. Now, at that time, they did not yet know exactly how far it was between the Earth and the sun. Matter of fact, the only knowledge they had at that time was to use the same methodology like they used back in the days of the Greek, when Aristarchus realized, according to his calculations, that the sun was about 4.5–5 million miles away. Of course, they didn't use miles, but I'm just translating in our units here, which of course is only about 1/20th of the true distance to the sun. They were beginning to think, modern astronomers back in the days of Kepler were beginning to think that that number may be off, but they were not able yet to come up with better methodologies to figure out the distance until about a decade or two later, after Kepler came up with his third law. But nevertheless, they at least realized that relative to the distance between the Earth and the sun, which is 1 astronomical unit, they then realized that Mars would be 1.5 times as far away. If they did the same calculation for, let's say, Jupiter, figuring that Jupiter has a period of about 12 years, then they say, well, the distance to Jupiter is equal to the cube root of, let's say, 11.86 squared. And when they, well, of course, they didn't have calculators back then, but they were able to work these out. So they took 11.86 squared, and they took the cube root of that. So the cube root of that is equal to, and they came out with 5.2 astronomical units. So that made them realize that Jupiter was 5 times as far away from the sun as the Earth, and so forth. And so all they had to do then is find better ways of measuring the distance to the sun, and they would then know the distance to the planets. So at this point, they just had a relative distance, but a few decades later, when they began to take more careful measurements and figuring out the true distance to the sun, and within the same century, if you saw some of the early videos, how they figured out how to do that, then actually had a fairly good idea of how far it was to the planets. Ingenious way. All it took was for Kepler to spend years and years and years studying those notes of Tycho Brahe and finally making sense out of them and realizing if the orbits of the planets are ellipses, then this third law of Kepler just fell out of that. And with a lot of hard work and a lot of studying, he realized that's the relationship. and now we knew the distance to the planets. So slowly but surely, we were able to figure out how big our universe was. In that time, of course, the universe was basically the solar system with the stars in the distance. But as we developed better and better techniques, we began to realize, wow, this universe is enormous. And so we're going to learn in the next so many videos how we figured out the distances to the stars, to the galaxies, and on beyond that. Welcome to that lecture online. Now that we learned in the previous videos how they figured out the distance to the moon, the distance to the sun, the size of the moon, the size of the sun, and the distance to the planets, and of course once they knew the distance to the planets and they could measure what we would call the apparent size of the planets based upon the angle that the planets would subtend, they could also kind of figure out the size of the planets. So they were beginning to figure out pretty well how big our solar system was. But now they looked up to those points of light up there, the stars, and already back in the days of Copernicus, when he came up with the conclusion that those stars were much, much, much farther away than the planets, they began to wonder, well, how far are those stars? How can we find the distance to those stars? They really didn't have any idea what they were. They didn't realize at the time that those stars were just basically other suns like our own sun, just much farther away, but they still wanted to know how far those stars were. But how do you figure out the distance of things when you don't know what they are and they seem to be motionless in the sky? Well, it turned out as they began to come up with better, bigger and better telescopes, and they started looking at the brightest of the stars, some of them actually showed that they moved a little bit in position relative to the other stars at different times of the year. And let me explain what that is. So let's say that the Earth is over here relative to the sun, and they were training their telescopes in this direction, looking at these stars right there. Now, even though the two stars may be very close together as far as angle is concerned, they would have no way that star 1 may be a lot closer than star 2. There's no way for them to tell. Maybe star 1 was brighter, but that doesn't mean it's closer, because it could be brighter just because it's a very bright star, and this could be dimmer just because it's a very dim star. It could also be because it's a closer star versus a farther star. They had no way of telling. So what happened though is that when they observed the very same stars, let's say 3 months later, when the Earth had moved in a different position over here, again being 1 astronomical unit away, they would then look at the same two stars, but notice now they would have a different position in the sky relative to each other, and they would be able to measure this difference in the angle between seeing the star from this position and seeing the star from that position. They would be able to measure these angles right here. Those angles are called the angles of parallax by looking at the same object from two different positions, and so you then have this different angle. Also notice that when the stars are closer, the angle of parallax would be bigger. If the stars are farther away, the angle of parallax would be smaller. And that would be the key to understanding how far these stars were. They would have to do is observe the position of the stars at this time, position of stars at this time, then measure the angle of parallax, and then from that they would be able to calculate the distance to those stars, understanding that the distance between the Earth and the Sun was 93 million miles. How did they do that? Well, it's that very same equation again. This distance right here, because you're seeing this is basically a triangle, so the distance of the base, small d, and then this distance right here called that large d, the ratio of that would be equal to the angle right here divided by the number of degrees in a radian. And so if we solve this equation for big D, which is what we're looking for the distance to the star, that would be equal to the distance between the Earth and the Sun, which is 1 astronomical unit, or 93 million miles. Then we have the number of degrees in a radian, and we divide that by the angle that we had measured. Now, of course, these angles are very, very small. For example, if the angle was exactly 1 arc second, which is 1/3600 of a degree. Remember, there are 60 seconds in an arc minute and 60 arc minutes in a degree, so it would be 3,600 arc seconds in 1 degree. So we take one of those arc seconds as a measurement, we divide that into the distance between the Sun and the Earth, multiply that times 57.3, which is the number of degrees in a radian, and out pops, of course, if we do a little bit of a conversion, we end up with 3.26 light years, understanding that a light year is about 6 trillion miles. So it then ended up being about 20 trillion miles, which is about 3.26 light years. And so there came the unit then that if the angle is 1 arc second, the distance would be 3.26 light years. And so they came up with this new distance unit called the parsec. Now, where does parsec come from? Well, par comes from the angle of parallax, and seconds comes from the unit arc seconds. So when they put those two together, 1 parsec, so we have a distance of the angle of parallax. When the angle is 1 arc second, the distance therefore is 1 parsec, and therefore 3.26 light years. Now it turns out there are no stars that are actually that close to us. The closest star is about 4.5 light years, so the biggest angle to the closest star would actually be less than a parsec. And it's very difficult with a telescope to measure those very small angles. So they had to have some pretty good quality telescopes at the time to be able to do that. But it turned out that in recent modern history, so for example 100 years ago or so, they were beginning to able to take angle measurements as small as 1/5 of an arc second, which meant that they could start measuring distances of stars as far away as about 5 parsecs or about 16 light years. And it turns out within a radius of about 16 light years there are about 100 stars. And so at that time they were able to measure the distance to the nearest 100 stars or so using this method, using this angle of parallax. One way in which you can kind of simulate how this method works is, let's say you look at an object that is not too far away, like let's say you put your pen in front of it, and you have another object that's farther away behind it. So you kind of angle it right towards another bigger object behind it, and then you look at it with your left eye, and then you look at it with your right eye, and all of a sudden you see the object jump. That's the angle of parallax. So try that, try it at home. So again, put a pen like in front of a corner of a wall or in front of a sofa or a television or something, and look at it with your left eye, and then look at it with your right eye, and all of a sudden, bang, the object switches, and that's what we mean by the angle of parallax. And if you have the object closer by, the angle will be much bigger, and if the object is far away, the angle will be a lot smaller. And that's what we mean by the angle of parallax. So the way the distance formula now works is that the distance in parsecs to any star is equal to 1 divided by the angle in arc seconds. So for example, if the angle in arc seconds is, and this would be in parsecs, right? So that would be in parsecs. And I guess we write parsecs as PC. So 1 PC divided by the angle in arc seconds. And let's say for our example, the angle is 1/5 of an arc second. That would be equal to 1 parsec divided by 1/5, which would be 5 parsecs. So you can see the equation is very simple after that. All you have to do is measure the angle in arc seconds, divide that into 1 parsec, and you know the distance. So far, 5 parsec is roughly about 16 light years. So that was very ingenious. Once they figured that out, they finally began to be able to measure the distance of stars in arc seconds. And imagine the amazement they would have had when they began to realize, wow, these stars are trillions of miles away. So that was an absolute amazing discovery. So now they realized, wow, the planets are just in terms of millions of miles away, but wow, the stars are trillions of miles away. So they now began to realize that, wow, the universe we live in is enormous in size. Of course, back in those days, they thought the universe now was simply the galaxy we lived in. We didn't know that was a galaxy. We just thought that this was just an enormous quantity of stars out there, because when they started looking at the stars with a telescope, they saw more and more and more of them. And then they began to realize that the distance just the nearest 100 stars was in the order of 10 or 20 trillion miles away. So that was quite a discovery, but yet still very limited, because now we wanted to know how far it was to these other stars out there. And then we began to see nebulas out there. We want to know how far it was to those nebulas. So again, the problem was still very daunting, but we're getting better and better at it with more and more discoveries. So on to the next tape and see what we discovered next. Welcome to Lecture Online, and now we're going to take a close look at how they figured out the distance of the stars beyond those that we could measure with the angle of parallax. If you remember in the previous video, we found out how they were able to measure the distance to the nearest 100 stars or so, simply because by measuring the position of the stars from various vantage points in the Earth's orbit, we could actually measure a difference in that angle, which was then known as the angle of parallax, which enabled us to find the distance to those stars. But that method was only really valid to the 100 near stars, because any stars beyond that, any stars beyond 15, 16 light years, had such a small angle of parallax that we could just simply not measure that angle. So how did we figure out the distance to the stars beyond that? Well, it turned out it was actually as a result of a number of things that we discovered, a number of the properties of stars, temperatures, wavelengths, things like that. So we're going to take a look at some of these to be able to understand how they've been beyond the angle of parallax to find the distance to even further stars. So the first thing we want to learn about is what we call Wien's law. Wilhelm Wien was a physicist slash astronomer slash scientist who was very intelligent, and he discovered that the radiation coming from an object could be determined if we can exclude all the other radiation. And he did that by developing what we call a black box. So what he did was simply take a box and he drilled a small little hole in it. Now, it really didn't have anything to do with the color of the box. But what happens is when you drill a small little hole in a box, even though the box inside may be painted white, and you look through that little hole, the inside of that box will look black. And the reason for that is because the radiation coming from the box is simply a result of the temperature of the inside of the box, not as a result of any light reflected that might have entered the box from the outside, because the hole is so small that by the time the light scatters around, almost none of it makes it back out, and therefore you don't see any light coming out, just the radiation coming out from the temperature of the inside of the box. And Wien was able to make a relationship between the wavelength of that radiation and the temperature of the box. And he also realized that the distribution of the radiation, because it wasn't a single wavelength of radiation coming from the box, it was a distribution of wavelengths. And the distribution looked like this. And this is what we know as a black body radiation curve, where some of it has smaller wavelength, some of it has bigger wavelengths. So the bottom of the axis here is wavelengths, the vertical axis here is intensity, so we call that the black body radiation curve. And he realized that there was this distribution of radiations coming from it, but at one point there was a peak, meaning one particular frequency or one particular wavelength of radiation was more abundant than all the other ones, and so he centered on that. And he said, I can find the temperature of this object by knowing what this number is. So if you can measure the radiation coming from a black body, and you figure out the peak wavelength, and you throw that into the equation that Wien came up with, where the temperature of the object therefore is equal to this constant divided by the wavelength, and that enabled him to find the temperature of that object. He received the Nobel Prize for that discovery in 1911 for work he did in the late 1890s. And so now, for example, let's say we take the sun, which the radiation of the sun is kind of like a black body. Now you say, well, wait a minute, the sun doesn't look black at all. Why can the sun be a black body? It's because the radiation coming from the sun is solely from the sun and not from scattering any light from any other source. The sun is, of course, so bright that there's no other light that can be reflected off the sun or scattered off the sun. So the radiation from the sun is purely from the source, just like the radiation from a black body is purely coming from inside the box and not from any light being scattered or reflected from anywhere else. And so when he applied that equation to the radiation coming from the sun, and of course the sun is a yellow star, and the yellow star has a wavelength, a peak wavelength of about, not 580 nanometers, it's more like about 500 nanometers. So make this 500. So if you then plug this number, 500 nanometers, into Wien's law, we should be able to figure out the temperature of the sun. And that's what he did. So he said, well, the temperature of the sun is equal to 0.0029 Kelvin times meters, divided by the wavelength coming from the star, which is 500 times 10 to the minus 9 meters. And when you work that out in your calculator, you get 5,800 Kelvin. Wow, that was quite a discovery. We're now able to determine the temperature of objects simply by knowing their radiation curve, their black body radiation curve. You might have noticed that when you have an electric stove at home, and you turn the plates all the way up to high, the plate begins to glow. As the temperature gets hotter, the radiation shifts to shorter and shorter wavelengths, and eventually it goes from the infrared into the visible wavelength, and red light begins to emanate from that hot plate. So that's an example of black body radiation. And so now we also began to realize that we have stars of different colors. And we also realized that for the stars of different colors, and notice I don't have a yellow pen, so I put the orange dotted line, and I don't have a white pen. Even if I had one, it wouldn't show up on the whiteboard, so I made a dotted black line there. So we had stars of these different colors, and we noticed that those stars would have different black body radiation curves. Stars that were redder would have curves that looked a little bit more like this. Oh, and it wouldn't quite go this high. I think I'm exaggerating this curve a little bit. Let me redraw that. it would look a little bit more like this. And then black body radiation curves of blue stars, it would look more like this. And you can see that the peak of the radiation would fall at different wavelengths. So red stars would have longer wavelengths, and blue stars would have shorter wavelengths, and white stars would have wavelengths in between, and so forth. So then we began to make that relationship, realizing that stars have different temperatures, and those temperatures are related to their colors, because stars put out what we call black body radiation, and the temperature of those stars can therefore be determined simply by knowing where the peak of the radiation is. And maybe what I should write here is lambda sub 0, that indicates the peak wavelength, just my way of indicating that. All right, so now we have another weapon in our repertoire, or maybe I should call it a tool. It's not a weapon per se, but a tool in order to determine the distance of stars. We now have the relationship between their color and their temperature. And now, coupled with another law, which is called the Stefan-Boltzmann's law, we now will have the information necessary to try and determine the distance to even further stars. So in the next video, we'll attack the Stefan-Boltzmann's law. And when we put those two concepts together, there were two very famous astronomers that came up with a very ingenious method to then determine the distance of stars even further than what we're able to measure with the angle of parallax. So if you're interested, stay tuned, and we'll show you some more of these interesting discoveries they made just about 100, 150 years ago.